No.
All right. Last time, where did we end up?
Justify this for HE.
Okay. So what were we trying to justify for HE?
Oh, the approximation that we could set, like we could separate each electron.
Yes, and do you remember what that approximation was called?
Orbital approximation.
Yeah. So in that one, we said we could separate the orbital or the electrons' motions from one another. So if we had a wave function that depended on the position of, let's say, 3 electrons, we could split that up into 3 separate orbitals that each only depend on the position of that specific electron, right? Okay, and what we were going to do next is we were going to justify this for the helium. Okay. So let's jump back to the Hamiltonian of the helium. What's that Hamiltonian going to be comprised of? Or could you tell me like the full formality of it?
Hamiltonian for helium?
Yep, the Hamiltonian for helium.
Negative H bar squared
Mhm.
over 2 mu.
Yeah.
Dorito E1 squared minus H bar squared over 2 mu. Dorito E2
Mhm.
squared minus 2E squared 4 pi E naught R1 minus 2E squared 4 pi EO R2.
And I know how you guys feel now.
And then E squared 4 pi EO R1 2.
Come on, you gotta keep up.
Imagine from my senior sound, I'm like donut with the sword. I would fail it instantly.
If you what?
If I pulled up like shark fin for something, or I said like donut,
That's trident, as we call it.
every other
that is
doctor would be
correct.
disgusted.
No, I bet you they would just look at you funny and then be like, oh, I don't know, maybe she's right, because like PChem is like a wizard thing for them. They just feel like, yep, there it is. Okay, so this is the Hamiltonian that we came up with. But now let's make this for like the orbital approximation. Oh, did I lose you guys?
No.
Nope.
Oh, okay, everyone was just frozen for a second. Just
I'm
smiling and
still
staring at me. I was getting weirded out.
Everyone just pretend to freeze. Ready? Just
Yeah, yeah, just don't move. Okay, so now for the orbital approximation, we have said that these things can be separated. So we need to rewrite this Hamiltonian in a way where everything's separated. So some things are going to have to change. We want to write it so we have just the parts that depend on electron 1 and parts that depend on electron 2. We want to represent this H1, H2, E1, 2. So what are these things? This is like the Hamiltonian for electron number 1. This is the Hamiltonian for electron number 2. And what's this last thing?
The potential energy
Yep, for 1.
of 1, 2.
Yep. So this is the electron-electron interaction. If we write this whole thing out, it's going to look almost like this, but we're going to lump these electron number 1 terms together. And these electron 2 terms together. So if we do that, get negative h bar squared to mass of electron, electron 1 squared minus 2e squared 4 pi epsilon r1. H bar 2me derivative for electron 2. 2e squared 4 pi epsilon naught r1. Plus e squared 4 pi epsilon naught r12. Okay, so some minor things have changed. Do you notice anything that has changed a little bit?
There's only 1 minus 2e squared. No, never mind.
Nope, there are two.
Yeah, never mind.
There's supposed to be 2 R1s.
Oh yeah, there. Well, yeah. If you don't screw it up, this should be. There you go.
Also, does the V1 of 2 have a 2e squared, or is it just e squared?
Nope, it's just e squared. Because this two actually comes from the nuclear charge of, excuse me, of the nucleus. Should that be a squared or should that be a 4? No,
No,
squared
it's
is
just
right.
z, so that would be 2.
Yep.
Not z squared.
So one other thing has changed, one little minor thing, the mass of the electron. So if you notice, it was a reduced mass up here. In this case, we have mass of an electron. So through that orbital approximation, we do that. Yeah. And if you notice, this is like the Hamiltonian of electron number 1. This purple portion is the Hamiltonian of electron number 2. And then we got the electron-electron interaction. Yeah. Oh, did I break up again?
Nope.
No? Okay.
Yeah.
You heard me?
Everyone just like half asleep right now.
Yeah.
I just zoned out.
No. There were definitely people not moving. So like,
I couldn't hear anything.
okay. So these Hamiltonians, they're each for each individual electron, right? So the red one is for electron number 1, purple one's for electron number 2. Okay. So now let's make the orbital approximation. So our wave function, what does our wave function depend on?
R, phi, and theta.
That is true, but in this case, we're going with an atom. We're saying it's spherical, so we don't have to worry about the theta and stuff.
Is it R1, R2, and R3?
Yep. R1 and R2, we don't have to worry about R3 because we're dealing with helium, only 2 electrons. So then we can say, all right, we have 2 orbitals. One that electron number 1 is occupying and one that electron number 2 is occupying. And what else does the orbital approximation say? Like what consequences does this have?
It means that each orbital occupies, or each electron occupies its own orbital, and they're
Right.
kind of independent of each other.
Right, so what needs to change with this thing up here? With that Hamiltonian?
Well, if they're independent of each other, then isn't the last term, don't you want to make that not relevant?
Yeah, we say that V12 is equal to 0. So that last term right here, that's 0. So therefore, our Hamiltonian is just comprised of the Hamiltonian of electron number 1 and the Hamiltonian of electron number 2. Cool. All right, so now let's show that this can actually be done. We take H. Oops, we don't need a parenthesis there. Of our wave function. Okay, now let's sub in what we're approximating. We have this orbital wave function, and we said our Hamiltonian is just made up of these two components. We have H1 hat plus H2 hat operates on phi R1 by R2. Okay, we can distribute this because our Hamiltonian, what do you remember about our Hamiltonian? What type of operator is it? Starts with an H.
Hermitian?
It's Hermitian.
Yep, it's a Hermitian operator. So we can wiggle that around. Like the other quantum mechanical word, Hamiltonian, Hermitian, got it. So let's apply this to each of these. So we get H hat 1 psi of R1, or excuse me, phi of R2 plus H hat 2 R1 R2. Okay, can we simplify this in any other way? Or what can we do now? Or if we have the H1 operator, is it going to act on this function at all?
No,
Why not?
because it's not relying on that radius.
Right. So if we look back up at this H1 and we look at the operator for it, it only depends on electron number 1. So what we could do is we could rearrange this. We can pull this guy out as a scalar or just out front because the operator doesn't impact it. Oops. R1. And then we can do the same thing with this guy, right? Because this Hamiltonian, it only influences orbital number 2. Okay, now what we're going to do is we're going to use a little trick. What is the generic form of the Schrodinger equation again?
H hat psi equals E psi.
Yeah.
Please use proper terms only.
Oh,
Trident.
yeah,
Sorry.
shark fin. Yeah, excuse me, shark fin.
Trident.
Yep. So now what we're going to do is we're going to put in some energies. We know that if this Hamiltonian operates on R1, what are we going to get out?
Energy of that electron.
Yep, the energy of that electron. We're going to call that E1 phi R1. Plus, what's the second term going to look like?
It's phi 1 E2.
Mm-hmm. Like that, right?
Mhm.
What do you know about these energies?
They should be equal.
Well,
Or
actually, yeah, they should be. Will they be? I guess it depends on the position of them. Right now, we're assuming the electrons can be in different positions.
I guess they could be equal, I guess, but then
Yeah.
again, that doesn't really do much.
Now, here we couldn't pull out this Hamiltonian, right? Because it has to operate on this function. Can we separate these two terms?
Yep.
Why?
Yeah.
Because you've already done your operation.
Yeah, you've already done your operation. This is just a scalar. This is just a number. So what we can do is we can pull out E1, E2. So we get E1 plus E2 times, we'll pull out that and that. And therefore, what we're saying is we're approximating the total energy of the system is equal to this, because we made that first step. So it looks like the orbital approximation does make mathematical sense, and where we can break apart our wave function if we're approximating this part to be true, and we end up with an energy of our system. But in reality, is this true?
No.
Right, and why not?
Because we made an approximation that the potential energy is 0 between
Yeah.
the two electrons, and that's not really the case.
Yeah, it's never the case. So this is only true. This is only an approximation. So like we've seen in lab where we use different approximations and get different answers, we have to do that to have something that is solvable. Okay, so that's about all we're going to talk about for the helium atom and 2 electron systems. Solving those equations, it's mathematically taxing, and you really don't get much more out of it. We've already talked about the ideas behind it. So we're done with that portion for the moment. We do need to talk about certain aspects that result from having a 2 electron system. And in order to do that, we have to talk about some mathematics or refresh some mathematics. We talked about matrices a little bit in inorganic, but we have to review them again. So have you guys ever heard the term determinant?
Yes.
Yeah, I think a couple of times.
You see them in linear algebra. You sometimes talk about them maybe a little bit in Calc 3, maybe a bit in differential equations. So what a determinant is it's a simple way to express a linear equation. A simple way to express a complex linear equation. I think formally what it's defined as is it's a scalar that represents a matrix. And you guys have sort of seen this before. So let's look at an example of a 2x2 determinant. Can anyone tell me how would we solve this determinant? So we have rows that go from left to right, and we have columns that go up and down. So how would you solve this?
So we're just trying to get a scalar out.
Yep, you're just trying to get a number out.
It would be AD minus CB.
Yep. So you take A and D multiplied together,
I know about matrices.
and then you subtract off C and B. So A times D minus B times C. Okay, everybody with me so far? You see the pattern? Okay, let's go to a 3 by 3.
Let's kick it up a notch.
Oh yeah, oh, don't worry, we'll get there.
What about 300 by 300? Let's just, why stop
How
here?
about 11 by 6? Isn't that how big your vine is?
Yeah.
You're like, how big is 11 by 6?
My roommate last year was like, guys, I got a 32-foot rug. And we're like, oh, that's pretty cool.
It's
And we thought
huge.
the whole thing, and it was the area. It was like
You're
the
like,
smallest
you're
rug
like,
I've ever seen.
square feet. You think that's big?
No, she was like so excited. She's like, I can't believe I got this great rug. We're like, okay. It was literally like 1 foot wide. Helco.
At her in the chat, I guess.
That's
Josh is her tutor.
Yeah, I was gonna
my
say,
wife
call her
in a
out.
nutshell. She
She's
has zero idea about areas. It's funny.
Yeah.
I don't know what she expected it to be. We literally were talking about like, oh, maybe we're gonna have to cut it to make it fit in our dorm. Like, okay, I'll get systems. No. I don't know how she didn't realize when she picked it up that it wouldn't be like big at all.
Sometimes no logic.
She's from Florida.
Explains it.
That is
Yeah.
the worst part about the coronavirus. I haven't seen any crazy news happening out of Florida lately. I'm a
Oh,
little
it'll start soon.
They're gonna start opening the beaches soon, and
It's
people
gonna
are
be
gonna
crazy as soon as they,
Yeah.
yeah.
All right, so anybody have an idea about this one? Okay, so what you do is you start with one of these terms in the top. So we have to start with A. And if you start with A, you exclude everything in that column. We would start with A and we would write a new determinant. So we exclude everything out of the top row and the first column. So what's this next determinant going to look like?
E,
Yeah.
F,
Yep, what is it? EF,
You
what
try.
else?
H, I.
Yep. What's gonna come next? Oops, actually.
B, F, D, I, G.
Yep, B, F, G, I, plus C, what's gonna be in that determinant?
E, E, G, H.
E, E, G, H, right?
Yeah,
How'd
why
you
is
go
it
from
minus plus?
But yeah, is that the
I'm
rule?
sorry, what'd you say, Tara?
Why is it minus plus? Why isn't it like minus minus or plus plus?
It just switches that way.
So the next one, if there's a D, it would be minus.
Yes, exactly. So we're gonna go to a 4x4 and show that. So now, what's this gonna look like? So we got A times what?
EI
Yep,
minus FH.
yep. Then we got minus B, what comes next?
DI
Yep,
minus FG
plus C, what comes next?
DH,
EH, yep, minus,
yeah, and EG.
yep, EG. Okay. Now let's move to a 4x4 and then we'll actually go into an example of this. Okay, remember, we always start with the first row. We select something in this row and we ignore the column of whatever term we selected. So let's start with A.
Would it be FGH,
Yep, FGH, what comes next?
JKL on the bottom?
Yep,
NOP. Nope.
yep, nope. Okay, what comes next?
Guessing
E.
minus.
Minus B, yep.
GH.
EG, H. What comes next?
IKL.
Yep. Followed by
Mop.
MOP, yep. Next one.
Be back to plus.
Yep, back to plus. C. What's going to be in that one?
EFG.
Yep, so we got E, F,
Oh, H.
H, yep. Next.
IJL.
J, L, yep.
MNP.
M, N, P, yep. Okay, next term.
Minus D.
Yep.
Is it
FG.
F?
Oops, sorry, I'm moving. Yep, so it's EFG,
IJK.
I, J, K, yep.
NO.
M, N, O, yep. And then I feel like you guys could go further with this and plug like that type of stuff in and solve, right? Everybody feel comfortable with that?
So you're just simplifying.
Yep. Yep. You just keep simplifying. The hardest thing with these types of problems is just keeping track of the sheer amount of data that you're dealing with. Try to write down as much as you can.
What's like the biggest one you would make us do?
100 by 100.
Whole final.
Probably like you could do a 6 by 6
A reasonable amount of time.
in a reasonable amount of time. What would happen is things simplify, and I'll show you that. It's not going to be dealing with hard numbers like our next example.
I want to see lots of zeros, just lots of zeros.
There's going to be lots of zeros and there's going to be lots of ones. If you remember back to a Quizlet, I had you like write out a matrix for wave functions and like to show if they, bless you, if they were orthogonal or not. And basically that diagonal was all ones and the rest were zeros. Same sort of thing's going to happen. If we're lucky. All right. So do you guys want to do an example, like a numerical example of that, or do you feel comfortable?
We're fine. We're not.
What example did you have planned? Just
Like example, evaluate the following determinant. Three, 4, 2, 1, 2, 6, 4, 4, 3, like that. You feel like you guys could do that?
Yeah.
Okay. Let's just go through and solve it pretty quick. What's the first term going to look like if this camera ever focuses?
3
Yeah.
times 2 times 3 minus 4 times 6.
Oh, I was going to do it this way. We'll get there. We'll get there in a second.
Slow down there.
Next term.
4 times
Minus 4.
3
Yep. Next term.
plus 2 and times 2, 6, 4, 3.
Oh wait, yep. 2, 1, 2, 4, 4, right?
Yes.
Because we got to ignore everything like that.
I don't know why, but
Okay. Now we got 3 times. What's going to happen to this stuff on the inside?
It's going to be 3 times 2 times 3.
Yep.
Minus 4 times 6.
Yep. minus 4, what comes next?
2 times 3 minus 4 times 6.
Yep.
That's not right, that one.
This one?
It should be 1, 6.
You're right, it should be 1, 6.
Good catch, doctor.
There we go.
It's what I do.
That's what I do.
Guessing?
Good work.
Oh, that should be a 1.
Yep, that one should be a 1. Oh, wait, no. We were right. Yeah, this one should be a 1. No.
I think she's
No, we were
no,
good.
it's 1643 for the second one.
Yep,
And the
yep.
first one is
Yeah,
664.
we're
Yeah.
okay. We're okay. I lied. I was swayed real easily. See?
Wait, is
Are
it
you sure?
The
Yeah,
second
but I
one
said,
should
don't
be
you try to
1.
make us not be swayed easily?
Second one, no, we were right. That should be a 1.
yeah,
Yep.
There we go.
it should be 1643. Okay.
Sheesh.
There we go. Yep.
Good.
1, 3, 6, 4. Yep. Then the last one.
2
1 times 4 minus 4 times 2.
Okay. So if you plug all that junk in, you solve. I think I should get 22. Okay. So despite me not being able to do the example, do you guys feel like you could do it?
Yeah.
I hope this is our whole next Quizlet.
Just nothing but these. Don't worry, actually, you're like
Amazing.
all the later stuff has to deal with doing things like this.
The whole quiz.
Yeah,
list-
but I know it's gonna be like matrices, but like it's gonna be a lot different than this.
Just be one giant matrix for the quiz. That could be fun. Cool. All right. So now that we've talked about determinants, what we're going to do next is we're going to discuss the Pauli Exclusion Principle in a little more in depth than we have in the past. So the next section is titled the Pauli Exclusion. Which we've talked about quite a bit. Can anyone describe the Pauli Exclusion Principle for me?
It's the spins, one has to be up, one has to be down.
Right. So the electrons have to have a different set of quantum numbers. They can't occupy the same quantum state. So no more than 2 electrons may occupy any given orbital and if 2 do occupy an orbital, then their spins must be paired. Basically, 1 up, 1 down, right? Okay. Or another way that this can be formulated is when you have the labels of 2 identical electrons. In this case, we're going to be more generic fermions. If you change them, then the sign of the wave function changes. Or when the labels of any 2 electrons, we're going to be a little more inclusive and say identical fermions are exchanged, the total wave function changes sign. And if we're talking about bosons, when 2 identical bosons are exchanged, the total wave function stays the same. So what this is saying is if we're going to consider a system that has 2 electrons in it. So consider the wave function of a 2-electron system. We have psi of 1, 2. So indicating that it's a wave function that depends on electron number 1 and electron number 2. If we interchange those labels, psi 1 of 2. What do we need to make this statement true? So we've switched the labels. If you look at what our definition is, what has to be true about this?
Becomes negative.
Yep.
Right.
Times negative. So that has to be true. So what we're going to do next time is we're going to show that this is indeed true. We need to use determinants to show that it's true. Okay? Are there any questions? No?